All right. Welcome everyone to, I think, lecture 5. As is customary, let me start the class just by asking if there are any logistical issues with how the class is running. I guess in particular, the problem set's due before next class, so hopefully everyone knows how to turn it in. Hopefully people are starting to go to office hours and make use of the TAs and course staff. Any questions about mechanics of the class before we get going? Okay. So to remember where we are in the story line we're sort of building up here. We've been trying to come up with like computationally plausible ways to make predictions in games. Okay, so we want to be able to talk about not just fixed points, not just stable states, not just equilibria, but paths, natural paths of play that might take us there. And so we studied congestion games, and we proved that a natural class of dynamics converges to equilibrium in congestion games. And sort of last class, we sort of said, okay, let's think about exactly when best response dynamics converges. And we gave a sort of characterization of the set of all games for which best response dynamics provides, like a convincing story of why you might end up playing a pure strategy Nash equilibrium, right? The class of games for which it's guaranteed to converge to Nash equilibrium. But we know, of course, that it doesn't converge to pure strategy Nash equilibria in every game. Can someone remind me of, like an obvious reason why? Yeah, rock, paper, scissors, rock, scissors. Yeah, got me. So like in particular, there's plenty of games that don't have pure strategy Nash equilibria. And since if best response dynamics converges, it converges to a pure strategy Nash equilibria, it can't possibly converge in games like rock, paper, scissors that don't even have them. And actually, it's not hard to notice that even in games that do have pure strategy Nash equilibria, best response dynamics need not converge, because you can have like a Nash equilibrium hidden away somewhere, but such that the path that best response dynamics takes you on doesn't lead you there. Okay, so like we can, cook up a game such that there's a game state over here that is a pure strategy Nash equilibria that everybody would love to be at, but such that when we look at, if you like, sort of this graph that we thought about last class that represents the set of trajectories that best response dynamics can take you on, right? This graph where game states correspond to vertices and edges correspond to best responses. We can cook up a graph such that, like most of the paths just don't lead to the pure strategy Nash equilibrium. So for example, we could embed matching pennies into sort of the 2x2 upper quadrant of this game matrix. We have like a Nash equilibrium over here, and maybe there's just like terrible game states everywhere else that basically prevent you from getting to the component of the graph that would lead you to the Nash equilibrium, right? So if you sort of draw out the trajectory of best response dynamics, what you'll find is that in sort of this matching pennies quadrant, you've got a cycle. And it's true that if you ever made it out here, it would take you to the unique pure strategy Nash equilibrium of the game. But if you start here, you know, best response dynamics is just not going to lead you there. Right, and you could sort of generalize this to larger games where, and you know, like this part of the game could make up almost all of its probability, all of the sort of mass of the game, so that almost everywhere you started, best response dynamics wouldn't lead you to the pure strategy Nash equilibrium, even if one existed. Okay, so it's not that best response dynamics tells us that we sort of converge to equilibrium whenever the game has a pure strategy Nash equilibrium. It's much more constrained than that. Like, as we showed last time, it's really got to be that the graph that you get when you draw something out like this doesn't have any cycles. So, you know, like in continuing our study of game dynamics, like the next step I want to take is I want to think about other things people might do in games for which best response dynamics maybe doesn't make a lot of sense. Games like rock, paper, scissors, say. Okay, so this is going to take us on a digression about sort of learning in games. Actually, really, for the next 2 lectures, just learning. We'll bring the games back sometime next week, right? But you know, I sort of want to think about reasonable things people could do in a game, even if they start out not knowing much about the game, right? Maybe that you're sort of thrown into a new situation. You know, the game might be complicated. Reasonable ways you might go about, or reasonable ways you might think about going about playing that game. Hopefully, you know, eventually leading us to statements about convergence to equilibria. But like, okay, so you know, our goal is to get to a sensible way of thinking about different players simultaneously learning in games. But the game part is going to just layer an additional level of complexity on there. You know, we're going to have like multiple people trying to learn things at the same time in a competitive environment. So for this class, and in fact the next class, I just want to abstract away the game and think about learning, period, in like a sequential decision-making environment. Right? Like like what does it mean to like learn in a game? Well, if we're playing a game repeatedly, like, you know, we're every day waking up and driving to work in a routing game or something. What happens is, right, like there's an aspect of time. I make a decision today, I make a decision tomorrow, I make a decision the next day. And so, oh, and there's an aspect of like payoff. Like I pick some route and it ends up, you know, it takes some amount of time for me to get to work, right? I observe like sort of some cost or payoff for the actions that I take, right? So there's this like sequential setting where I need to choose amongst some set of actions and I get some payoff. And I want to think about what's a good way to choose actions as a function of like my experiences so far. And eventually we want to think about like n-player games where everybody is simultaneously doing this and the payoffs are a function of what everyone else is simultaneously doing. But like, just to get ourselves used to thinking about these kinds of things, for today, I want to abstract away the game and just think about like learning in a sequential environment and figure out what that means. Okay, so that's like the overview for today. Questions about the story arc so far? Things that we've done and will do? Okay. So we're going to sort of, so eventually I want to build up to a theory of learning in sequential decision-making environments that is rich enough that it makes sense to sort of take a learning algorithm developed in one of these environments and just say, okay, we're going to play this learning algorithm in, you know, like an arbitrary game. So it should be able to talk about general action spaces, general sort of payoffs for different actions that you get. But let's start simple. Let's start with sort of a toy version of the model we're eventually going to develop and I'll describe it as sort of a toy model of stock prediction. Okay, so say there's like one stock you're interested in, maybe GameStop, And every day, it's going to go up or it's going to go down. Okay? You don't know which one. And your goal is before the market opens, you would like to just predict the direction that it's going to go in, just like a binary decision, up or down. Right? You could imagine in a richer version of this, you want to predict something, a little bit more precise. But let's just start by saying you want to predict the direction, up or down. So you want to take like a long or a short position in this stock to make money. And the problem is it's like hard to predict in stock markets. Like the stock market is not necessarily following a well-behaved statistical process. And so we don't want to assume that it is if we sort of develop theory that only applies under very specific assumptions for how the stock market's going to evolve, our theory is probably going to be wrong. So we sort of want to assume that the stock market, this sequence of ups and downs can really behave arbitrarily. And one way to model arbitrary behavior is by thinking about it as generated by an adversary. So we're going to want to come up with some method for learning in this environment that will have some guarantees. And whatever those guarantees are, we would like it to hold, even if the sequence of observations made by the algorithm is chosen, adaptively by an adversary whose only goal is to try to falsify the guarantees of the algorithm. Okay, so if you've taken a machine learning class, this is sort of very different from the typical setup for statistical learning. Right? In the typical setup for statistical learning, you assume there's a distribution and you've got data points that you get to train on that are sort of well behaved. They're sampled IID from some distribution, and the goal is to use the data to learn some statistical regularity about the distribution that will give you some predictive advantage on new data so long as it's drawn from the same distribution. There's no distribution here. Okay, we're going to define what is in some sense a very difficult learning problem, because there's no assumption that the things you've seen in the past, there's no assumption that the past will be reflective of the future here. An adversarial data sequence can change in arbitrary ways all the time. Which means that if we're going to try to prove something interesting about an algorithm, we have to be measured about what our goals are. Our goal cannot be to make a lot of money. Our goal cannot be to predict, to guarantee that no matter what the sequence is, that we predict correctly, most of the time, right? Because, for example, it could be that what happens is, maybe the adversarial sequence is going to be really simple. Maybe every day the adversary is just going to flip a coin, and the stock market will go up or down, at random. There's no way you can predict, there's no method to predict correctly more than half the time in that case. Okay, so in the kind of model we're setting up, it's just not a sensible goal to say that we want to do well in any kind of absolute sense. We're going to have to think about performance relative to some benchmark class. Okay, so as stated so far, it seems like there's little interesting you can do in this model. If you don't get to observe anything, you just have to make predictions based on nothing, then what can you do? So there's a little bit more in the model. You do get to observe something before making your predictions. And one way that is useful to think about it for now is that before you make your prediction every day, you get a little bit of advice. Okay, we'll call this the sort of expert advice model. Okay, so remember, it's like this sequential binary prediction problem. Every day you predict up or down, then you're going to learn, did GameStop go up or down? And so, okay, what's the expert advice aspect? Well, every day before the bell rings, opening the market, before you need to make your prediction, these N self-proclaimed experts come over and whisper something in your ear. They say, I think the market's going to go up today, or I think the market's going to go down today. There's N of them. Now, okay, like the terminology, we call these people experts, but like they're self-proclaimed experts. Like think about these just as Wharton students or something. Like they have strong opinions maybe about what the stock market's going to do, but that doesn't necessarily mean that they're right. Okay, like if they were all like financial geniuses, it would be like easy. They'd probably all agree about what to do, and you would just do that. That's not the problem. Like the advice of, not only is the sequence of outcomes, up or down, going to be arbitrary, the predictions every day of the experts are also going to be arbitrary. Like it might be that there's some good experts. It might be that there's some not so good experts, and you certainly don't know who is who. And so, like, because in an adversarial setting, it doesn't make sense to talk about doing well in an absolute sense, we would like to set up a goal that frames doing well as in sort of a relative sense. Okay, so our goal is going to be to aggregate the expert advice, meaning like we need to design an algorithm that listens to these n experts every day, thinks about the advice, maybe also thinks about the history of what's happened so far. We can look at their track records and maps that to a decision about how we're going to predict every day. And our goal is to do as well, or almost as well, as whoever turns out to be the most accurate expert in hindsight when all is said and done. Okay, so this sort of gets around the problem of what happens if stocks are just a coin flip. Of course, if whether GameStop goes up or down, it's just a coin flip. We can't predict better than 50%, but neither can the experts. So we can achieve the goal of doing as well as the best expert in hindsight. But of course, if we promise that no matter what happens, we do as well as the best expert in hindsight, if it turns out after the fact that there was some expert who actually did know what he was talking about and did pretty well, then in any instance like that, our guarantee would obligate our algorithm also to do well. Okay, so this is sort of a relative performance goal that makes sense to ask for even in the worst case without assuming any kind of like distribution of our observations. Okay, so questions about the setup here? Yeah. Oh, no. So the information, we'll formalize this all in a moment, but like, when I say we aggregate expert advice, I just mean the algorithm we need to design, even though it gets the input of these n experts, ultimately it needs to commit to a single prediction. But in figuring out what that prediction is, it can look in as granular a way as it wants to the sequence of predictions made by these experts. So it's like you can do things like evaluate how frequently the expert was right in the past. Yeah. In principle, sometimes you could, and these are good questions. In the worst case, you can't, because again, like if the thing you're trying to predict is a coin flip, then all of the any prediction method will produce a correct prediction 50% of the time, and so there's no way to do better than that. So you can't. There's no way to promise that in the worst case you do better. There's no way to promise that in the worst case you do better than the best expert, but there are ways to try to formulate goals that maybe on particular cases that have structure that you do better than the best expert. Yeah. Yes. So again, we'll formalize this all in a moment, but you're right. So first of all, best means, in this setting, since we're just, guessing this binary outcome, how frequently were they right? We would like to be right as frequently as the best expert in hindsight. And the reason I say in hindsight is because there's no distribution. So it doesn't make sense to sort of say ahead of time, like this fellow, Jimmy, is the best expert, because that may not be the case. It is only after this, after our algorithm has sort of interacted in this scenario for t rounds, and and when we can sort of look back in time and see, given what actually happened, who turned out to be the best expert. Good question. Yeah. That's right. So if I look, at some prefix, if I look at the first 100 rounds, the person, the expert who's the best expert at round 100 is not necessarily the person who's the best expert at round 1000, which is something the algorithm in general is going to need to be able to grapple with. Other questions? Okay. Okay, so already this is sort of like a toy version of the problem we want to solve, because like there's only two, it's just a binary prediction problem. But just so we can develop some intuition for like what these algorithms might look like, I want to make the problem even easier. And so our goal over the next two classes is going to be to sort of start with a really stripped down toy version of the problem for which the algorithm is not difficult. In fact, I'm just going to ask one of you guys in a moment to tell me what the algorithm is. And then we're going to try to complicate the scenario and try to solve that. And each new solution will be hopefully familiar, given that we know the solution to the easier problem, until before we know it, we get an actually useful algorithm. So I want to start with an even easier case, and it's related. I'm going to make it easier in a way that's sort of related to the question that was just asked about whether the expert who is best at round 100 is also going to be a best expert at round 1000. Okay, so here's the easier case. So we've got these n experts, capital N, who are going to make predictions in some number of rounds, capital T rounds. Okay, and just to sort of put some notation to this, to start writing down a formal model, at every round T, each expert I will make a binary prediction, which I'll denote by PIT, and it's just, it's a binary prediction, but let's say it can take value up or down. And we, the algorithm, get to look at the history of all of the predictions and outcomes so far up to, but not including day T, and decide how to, and of course we get to observe the predictions at day T as well. And then we, the algorithm, have to commit to our own prediction, up or down. I'll call that PAT. And only after we commit to our prediction do we learn the true outcome, which I'll denote OT, and that's also a binary outcome, up or down. GameStop goes up or GameStop goes down. And it might be that we make an incorrect prediction. That would, when I say we make an incorrect prediction or we make a mistake, I just mean that our prediction was not equal to the outcome. If our prediction was equal to the outcome, I say we made a correct prediction. And this is the way we're going to make things like even easier as a first cut. Although in general, the sequence of predictions can be arbitrary, and as can the sequence of outcomes, I want to start off by assuming that there's one perfect expert. Like there's someone out there who just like knows how the world works. This expert is guaranteed never to make a mistake. Okay, so like if we only followed this expert's advice every single day, then we too, the algorithm, would never make a mistake. And of course, we have access to this expert's advice. He's like whispering it in our ear. The only problem is we don't know who he is or she, right? So there's like this expert, there's this, this expert who is out there, but in this pool of n experts. I know one of them is perfect. One of them is guaranteed never to make a mistake, but there's these n-1 others who I still know nothing about. Okay, I'd like to do as well, almost as well as the best expert, which in this case means, like making as few mistakes as possible, because the best expert is guaranteed to make 0 mistakes. And the only difficulty that I have is that I have no idea who is this perfect expert. Okay, I somehow need to like discover that as the algorithm goes on. Okay, so I claim that in this simple stripped down version of the problem, there is a very simple intuitive strategy that is guaranteed to make at most log n many mistakes, where n is the number of experts. Can anyone tell me how to do it? Yeah. Yeah, that's a pretty good idea. So let's think this through. So you're saying, okay, like I know that there's a perfect expert. And so if I ever observe someone making a mistake, I can just like immediately eliminate them from consideration. They can't possibly be the perfect expert. And at any given moment, there might be a bunch of people who have never yet been observed to make mistakes, and they might make different predictions about what I should do. And so I need to like figure out what to do from this pool of predictions, and you're suggesting going with the majority. And why is the majority a good thing to do?
Because like when they're wrong, you want to like eliminate it.
Yeah. Good. So let's follow through on this idea. It's called the halving algorithm. And I think the name of the algorithm is suggestive of the analysis. And it's exactly what we were just discussing. Okay. And it's a very intuitive thing to do. So what we're going to do is we're going to keep track of all of the experts who have a perfect track record so far. Initially, that's everyone. So this set S that we're going to maintain over the course of the run of the algorithm is just, at day t, the set of experts who have never yet been observed to make a mistake. Okay, this is initially everybody. This is also how I grade this class, by the way. I have a list of everyone who's never made a mistake, and then I just cross names off the list as problem sets come in. And so at every round, I need to make a prediction, right? These experts like are whispering in my ear, up or down. And I know that I don't, like if anyone has been observed to make a mistake, like they're out of there. Like I'm not going to listen to them at all anymore. But like I have this pool of experts that haven't yet, proven themselves to be flawed, and they might nevertheless disagree about what I should do today. And so I'll just like partition them according to what their predictions are. I'll say, STU, those are the sort of set of surviving experts at day t who today predict up. And STD, those are, a better name for that one. But that the other set is the set of experts who are the remaining experts who predict down today. And I just go with majority vote. So if more of the surviving experts predict up than down, I will predict up. Otherwise, I'll predict down. And then I learn what happened. Okay, like I see the outcome, up or down. And I will now eliminate all of the experts who were wrong. So in particular, if the outcome was up, then the set of surviving experts tomorrow is equal to the set of surviving experts today who predicted up. And otherwise, the set of surviving experts tomorrow is equal to the subset of surviving experts today who predicted down. Right, so the invariant that I'm maintaining is that the set ST, the set of surviving experts at day t, is the set of experts who have not yet been observed to make a mistake. Okay. Is the algorithm clear? Okay. So the claim is that under this very strong assumption, yeah. Good. So let's like be clear about the setting. There's no randomness here. So there's nothing to take an expectation of, right? Like the algorithm is not randomized, the algorithm is deterministic, and we are not assuming that the outcomes or the predictions of the expert follow any kind of distribution. Those can both be arbitrary. And so, you know, what this really means is that in the worst case, over any possible sequence of outcomes and any possible sequence of predictions for the n experts, so long as there's one expert who never makes a mistake, the algorithm makes at most log n many mistakes. So in the worst case, over all possible playouts of this interaction, we promise that our algorithm makes at most log n many mistakes.
Are you able to cut it in half each time? Like what if there's one perfect one and everyone else gets them all right except for like...
Oh, that would be great. Oh, good. So this is like another thing that maybe is sort of useful to reflect on. So like, in order to do well, we don't have to identify like who is the perfect expert, right? Like it might be that what happens is exactly what you described, that, you know, well, okay. Like maybe a couple of things to note. So it's like first, it might be that everyone is right every day, in which case we never eliminate anyone. But also that was kind of the right thing to do because everyone turned out to be perfect. It might also be that almost everyone is right every day. Like maybe every day, you know, there's only one expert who makes a mistake. Now, of course, we do eliminate the expert who made a mistake every day, but, you know, like you might be thinking, okay, but like there's n experts, I'm only eliminating one every day. Isn't this gonna like take us n days to find who's the perfect expert? And the answer is yes, but the theorem is not about like how long it takes us to find the perfect expert. It might be that we never, you know, it might be that we never sort of end up with only one remaining expert. The theorem is about how many mistakes we make. And if you think about it, right, like every day we're going with the majority vote. So if there's only one expert that's wrong every day, it's true that we're only eliminating one expert from the set each day, but we also never make a mistake. Okay, so in like that, it's like that's a good scenario. Like there, actually, we would do better than the promise of the theorem. We would make 0 mistakes. The runtime of the algorithm, as written, is n per iteration because we have to, if nothing else, you know, like listen to each of the n experts. Yes, so this is not a running time statement, although this algorithm is, you know, simple to implement. This is a statement about the number of mistakes it makes. Yeah, so this will come up later, actually. Like even in the more sort of sophisticated settings that we'll study, you know, we'll be able to get sort of performance bounds that depend only logarithmically on the number of actions. But in general, even to sort of think about a set of n actions, we're going to need running time that's like linear in n. Good questions. Okay, so good. So we're like already like asking questions that are sort of getting us towards a little bit how the analysis works, right? Like, because of course, like it could be that we quickly eliminate experts, and you know, like you could imagine a world where like after, you know, we cut the number of experts in half every day, and after like log n many rounds, we know there's one perfect expert, and you know we know who it is, and we can never make a mistake again. But like that doesn't have to happen, right? Like it could take us, even if there is only one perfect expert in the end, and every day someone makes a mistake, it could take us as long as n days before we figure out who it is. We just need to make sure that no matter which of those two things happens or something in between, like we don't make very many mistakes. Okay. So here's the key idea. because the algorithm is predicting according to the majority vote of the remaining experts, if the algorithm makes a mistake at some round t, the reason is because at least half of the remaining experts made a mistake. Right? Like if fewer than half of the remaining experts made a mistake, then the majority vote would have been correct. And so we don't need to worry about those rounds if we're just counting mistakes. So any round at which the algorithm makes a mistake means at least half of the remaining experts made a mistake. And so in particular, if I look at some round t, and you tell me the algorithm made a mistake at that round t, then I know that the number of remaining experts at round t plus 1 cannot possibly be larger than half of the number of remaining experts at day t, because I eliminated at least half of them if the majority vote was wrong. On the other hand, and this is sort of where we're using our sort of toy assumption here, that there's a perfect expert. Like I know for sure that there's at least one expert who is never eliminated. And in particular, I know like at every round t, the number of surviving experts is at least 1, because I never eliminate the perfect expert. And I know how many experts there were to start. There were n. Okay, so I start with n things. Every time I make a mistake, I cut the set of things at least in half. And the set of things the size of the set of things never goes below 1. So, how many times can I cut a set of size n in half before it must, like end up below 1? Well, at most log n many times. Okay, so the algorithm makes at most log n many mistakes, even though it might take many more than that rounds to like identify who is the best expert. Okay, like we don't need to identify who's the best expert. It's sort of like a win-win analysis. It's like either the algorithm did well at this round, or if the algorithm did poorly, we made progress towards identifying the best expert. We only need one of those two things to happen to get a theorem like this. Okay, is that clear? Yes.
Why is it only in the case that you make a mistake that we're triggering elimination?
Oh, no, we're eliminating every round the experts who made a mistake. We could eliminate people even if we don't make a mistake. And we are sort of pessimistically just not accounting for that in this analysis, right? It might be that the size of the set of remaining experts actually goes down more quickly than we're accounting for. But on rounds when we don't make a mistake, we can't say anything concrete about the rate at which we are making progress. We could have eliminated nobody if all of the experts were correct, or we could have eliminated as few as one person, even if some of the experts were wrong. So like, it's only when we make a mistake that we can sort of say that we are making like fast enough progress to get like a log n bound. And there are sequences where this is exactly what happens, right? It's the sequences where basically for the first log n rounds, yeah, like what this theorem is saying, the form of this theorem is it's saying in the worst case over instances, the algorithm cannot make more than log n mistakes. So the worst case, it's an instance that's both a sequence of stock outcomes and a sequence of predictions, one for each of the experts. And so we prove in the worst case it's log n. And there actually is an instance that causes that to be the case. So you couldn't improve this theorem to say log n over 2, for example, right? And the worst case is where actually, the bare majority is wrong every round, and really you make a mistake for the first log n rounds, and you really do cut the set of surviving experts exactly in half each time. Yeah, so the question is, you know, on the one hand, say the algorithm makes m mistakes. Okay, so like on the one hand, like we're thinking about sort of the cardinality of S capital T. How many experts survive at day t? Well, on the one hand, we know that this is larger than 1 because there's one surviving expert. On the other hand, we know it's smaller than what? Well, it's smaller than n, the number of experts we started with, times 1/2 to the m, because every time we made a mistake, and we made m mistakes, we cut this in half. And so if you solve for m, you get log n. Make sense? Good questions. Other questions? Okay. So we can ask ourselves, like, is this bound any good? And of course, you know, like there's like qualitatively and quantitatively. So like qualitatively, it kind of sucks because we made like this ridiculous assumption that there's a perfect expert, right? Like we're, you know, if anyone is ever observed to make a mistake, we just eliminate them from consideration immediately, which only makes sense to do if we know, if we're really confident that there's someone who's like never going to make a mistake. But quantitatively, it's pretty good because log n is a pretty small, you know, pretty slowly growing function of n. And when you think about these sort of relative bounds, right? We're saying sort of the bound is doing, you know, the algorithm is doing, you know, as well as the best expert. That's a stronger thing to say the more experts there are, right? Like the more experts there are, the more difficult it is to compete with this benchmark, right? Like as I start adding experts, maybe some of them are going to be good. And so since the sort of mistake bound grows only logarithmically with n, that means it's relatively cheap to compete with a very expressive benchmark class, right? Like I could, if I have 1,000 experts, then log n is 10. But like if I have 1,000,000 experts, log n is 20. And you know, in some sense, there's a much better chance that like 1,000,000 experts will have a good one compared to 1,000 experts, right? I'm promising to do as well as the best expert. So on the one hand, right. So on the one hand, like in order for the algorithm to even apply, we have to assume something crazy. On the other hand, like the numerical bound is pretty good, and we can sort of cheaply add lots of experts, you know, in some fuzzy way, probably like increasing the chance that we have a perfect expert somewhere in our set. And also, the bound doesn't grow with t. Right? We could play this interaction for 1,000 rounds, or 1,000,000 rounds, or 1,000,000,000,000 rounds, and the bound remains log n. So even if we have like a huge number of experts, if we look at the average number of mistakes made by the algorithm as a fraction of time, right? Like, you know, the rates at which we are making money on the stock market as a fraction of time, the difference between our performance and that of the best expert on average goes very quickly to 0 at the rate of 1/t. Okay. So these are sort of, you know, obviously we're gonna, in order for this to be a useful algorithm, we're gonna have to, you know, have some analog of this in a much more interesting model. Like right now, this is a toy model, especially this assumption of a perfect expert. But like quantitatively, there's a lot to like about this style of bound, that our error grows only logarithmically with the number of experts, and that our average error over time goes to 0. Yeah. Yeah, so like this is saying in some absolute sense, independently of how long we, like say there's 1,000 experts, independently of how long we run this prediction game, we will never make more than 1,024 mistakes. Or sorry, if there's 1,000 experts, we'll never make more than 10 mistakes. So if I look at the fraction of rounds I made mistakes on, if I run it for t rounds, the fraction of rounds that I make mistakes is going to be at most 10 over t. And so as t grows large, if I look at like my average performance, like what is the chance that I make a mistake on a randomly chosen day amongst all t of them, that goes very quickly to 0. Like a worse bound would be that, you know, you make log n times t mistakes, or that wouldn't make sense, but like, you know, 0.1 times t mistakes. That would mean that you're always making mistakes sort of 10% of the time on a randomly chosen day. As t grows large, here the chance that you make a mistake on a randomly chosen day as t grows large goes to 0. Okay, so that's another property that we're going to try to like maintain as we work in more complicated settings. Other questions? Okay. So let's try to take just one baby step towards a more sophisticated algorithm. We'll get there next class, but right now I just want to consider sort of a baby step on the way. Okay, and so like eventually there's a bunch of things we want to like generalize here. Like we don't want this to be like a binary prediction problem. Like we want to be able to choose amongst, you know, sort of arbitrary collections of like actions in a game. For now, like I'm gonna keep the sort of binary prediction aspect, but I just want to say, okay, like suppose there's no perfect expert. Nevertheless, just as I can sort of like after the algorithm halts and I see what were the historical predictions of all of the experts, I can still identify who was the best expert, and I can give a name to the number of mistakes made by the best expert in hindsight, like opt. Can we come up with an algorithm that guarantees that it doesn't make too many more mistakes than opt? Okay, so I want to sort of I want to be able to prove a theorem that sort of compares the performance of my algorithm to opt, even, and like sort of we've done that when opt is 0, and now I just want to get some version of that when opt is not 0. Okay. So maybe let's start by looking at our existing algorithm and just thinking about what would happen if we ran it without a perfect expert. Okay, so maybe we can just analyze this algorithm in a world in which there's no perfect expert. So like what happens if I run this algorithm and there's no perfect expert? Yeah, like it's not a matter, like it's sort of, it's not just that this algorithm like might not do well in that setting, like the algorithm might just like crash and fail to run at some point, right? Like this algorithm is doing something pretty severe. It's like entirely eliminating from consideration any expert that is ever observed to make a mistake. And so this algorithm will run fine, but like at some point you might find if there's no perfect expert, you've eliminated all of the experts from consideration, at which point it's not even really clear that this algorithm is like well defined. What does it mean to take the majority vote of an empty set? And so yes, so like there's a problem here, which is just that like more basic than that this doesn't get a good bound. It's more like if you run this algorithm in the setting where there's no perfect expert, it might just crash. Okay, but many of you are computer science majors at some advanced stage of your education, so you know what to do if you have like a program that's crashing. What is the like universal solution for this? Yeah. Yeah, like exactly. Like try again. Like turn it off and turn it on again, right? Like if eventually, like if your computer's messing up, just restart it. If we teach you nothing else, after 4 years at Penn, it's like restart your computer. So let's do that. Okay, so that's the proposal. That's our like main algorithmic idea here. We'll run this algorithm, the halving algorithm, and like it might crash at some point because we eliminate all of the experts. And if it does, I propose that we just like restart it, just like from the beginning, like put all of the experts like back into the bucket and forget the entire past history and start again. So we'll call this the iterated halving algorithm. And it is exactly the same as the halving algorithm, except it restarts itself when it crashes. Okay, so just as before, it's maintaining a set of all of the experts who have never been observed to make a mistake, at least since its last restart. At every round, it divides the experts into 2 bits, so long as there are any experts that remain, those experts that predict up and those experts that predict down. It goes with the majority vote. If there's more experts than that predict up compared to down, it predicts up, otherwise it predicts down, and anyone who is observed to make a mistake is eliminated. The only line of this algorithm that is different is like, the algorithm like crashes and you just push some like patch, just says, okay, if there are no experts remaining, like totally reset and promote everyone to, full status once more. Any questions about like what the algorithm is? Okay. So to start off, I mean, obviously this is a pretty dumb algorithm. And so it's not, like it's not gonna, we're not gonna be able to prove a great bound for it. Like we're gonna prove great bounds for different algorithms that we'll analyze next class. But I sort of want to start off by like showing we can prove some theorem relating the performance of an algorithm to the performance of the best expert, even when the best expert is not perfect. And in particular, I want to prove this theorem that says, well, look, in the worst case over any sequence, in the worst case over any instance, so in the worst case over any sequence of stock outcomes and any sequence of predictions of the n experts, if in hindsight, the best expert turns out to have made opt many mistakes on that sequence, then we can promise that the algorithm, this algorithm, the iterated halving algorithm, will have made at most log n times opt plus 1 many mistakes. Okay, and this is like just a generalization of our prior theorem, because if opt is 0, if there's a perfect expert, this is again telling us the algorithm makes at most log n many mistakes. But now, like the theorem is no longer vacuous, even if opt is not 0. Okay. So in the spirit of making you guys do all the work, how do I prove this theorem?
After it resets, like it'll hit this, the set will be empty after log n times, and then it'll only reset off this one time.
Yeah, so I think that's the right intuition. There are other details we might want to add here.
The worst possible case, everyone wants to make their errors, and it's like the last person left
mistake only makes there. So the log n errors, then this perfect person makes one error, and then you set.
Yeah, although like it's not necessary, like there's like we don't know the sequence in which the errors are made. Like it's not necessarily like the best expert is the last man standing every time. But that is the general idea, to try to sort of think about this as a race between the algorithm and the best expert, and keep track of what happens every time the algorithm makes a mistake and what happens every time the number of mistakes made by the best expert goes up. So every time opt increases. So right, like there is no, but like as we sort of discussed, when the best expert is allowed to make more than 0 mistakes, it doesn't make sense to sort of talk about the best expert until the end of time. There is no well-defined like best expert at round 15, because we don't know if they're going to be, if they're going to continue to be the best expert. So we can't quite, as the algorithm is running, compare ourselves to the best expert, but we can compare ourselves to opt. Like opt is a quantity that is sort of, we can keep track of and is like monotonically increasing with time. And we sort of want to argue that every time opt goes up by 1, we can't have made up, every time opt goes up by 1, we can have made at most log n mistakes. That's the kind of thing we want to argue. Okay. So remember, this algorithm is literally just the halving algorithm, but we restart it when it crashes. So everything we said, for the most part, about the halving algorithm remains true here. So it remains true that whenever the algorithm makes a mistake, we eliminate at least half of the experts in the current pool, right? Because we go with the majority vote. And so if we make a mistake, the majority vote was wrong, which means the majority of the experts were wrong, which means the majority of the experts are eliminated. And so we can sort of, like our analysis doesn't carry through, our analysis from last time doesn't carry through the whole algorithm because we reset it sometimes, but like it still carries through between any 2 resets. Right, like it's still true that between any 2 resets of the algorithm can make at most log n mistakes, because between any 2 resets, if we haven't yet, if I think about the starting point after 1 reset where I have n remaining experts, well, like if at round t I haven't yet reset the algorithm, I know that there's at least 1 expert remaining, because if there wasn't, I would have reset the algorithm. And I know that every time I made a mistake, I cut the number of remaining experts in half. And so that can't have happened more than log n many times before I triggered a reset. Or said another way, there must be a reset triggered between, like every time I make log n mistakes, there must be a reset triggered, right? Because I would have eliminated all of the experts in that time. On the other hand, I claim that if we have to reset the algorithm, it is because in the intervening time between the last reset, every single expert had made a mistake. Right? Because, at the last reset, all of the experts remained. At the next reset, none of them remain anymore. They've all been eliminated, so they've all made a mistake. So between any 2 resets, the algorithm makes at most log n many mistakes, and opt goes up by at least 1. Whoever, and in particular, whoever will have at the end turned out to be the best expert must have made a mistake between any 2 of the resets, because every expert made a mistake between any 2 of the resets. And so that gives our bound, right? We just sort of, look at, we look at the sequence of resets, right? If we think of play progressing along some timeline, and every once in a while, we reset. We have, on the one hand, the algorithm making fewer than log n many mistakes in each of these blocks between resets. On the other hand, the best expert making at least one mistake between each of these blocks. If there were k resets, there's k plus 1 of these blocks. And so the best expert can make at most log n times, well, the number of resets plus 1, which is at most opt plus 1. Okay, does that make sense? Yeah.
Clarify how we get at most log and like what exactly is that?
Why we make at most log n mistakes between resets? Yeah, so it's like this observation again. So like at the beginning, like say I make, the first reset. Okay, at that moment, there are n experts. And so now I want to think about what happens every time I, the algorithm, make a mistake. Well, I, the algorithm, make a mistake. If I, the algorithm, make a mistake, it is because the majority of the surviving experts made a mistake. And so every time I make a mistake, I eliminate at least half of the surviving experts. And since I'm looking at the time between resets, I know that in this time, I haven't eliminated everybody. The set of surviving experts has size at least 1, because if I did eliminate everyone, I would have triggered another reset. So, on the one hand, at any moment in this time between resets, the number of surviving experts is at least 1. On the other hand, the number of surviving experts is at most n, the number of experts I started with, times 1/2 raised to the power of the number of mistakes my algorithm made. Because every time my algorithm made a mistake, I cut this set in half. And so how can that be true? Well, just solving, I guess it's got to be that log of 1/2 to the m is at least 1 over n, or in other words, m is less than log base 2 of n. Or just, like more simply, I can't, if I have like n things, I can't cut that set in half more than log n many times before I have only one thing left.
So would the best case scenario be that like n minus 1 of the experts say, let's say up, and you go with that, but it's really down, then you eliminate the n minus 1.
You're saying everyone's wrong except 1?
Yeah,
That would be, well, I guess the best case scenario would be, the majority is always right. Then I never make a mistake. If the majority is always right, I never make a mistake. But you're right, it's also pretty good if everybody's wrong except for one person. Then I make tons of progress in figuring out who is the best expert. Like the core to this kind of argument, and this, we're going to use this again for more sophisticated algorithms next class, is that there's like 2 ways to do well here. Either you can not make mistakes, then you're sort of directly contributing to the objective of not making too many mistakes, or you can make quantifiable progress in some way in like identifying who is a good expert. And like the core for these kinds of arguments is that although we can't promise that we always make progress in identifying who's a good expert, and we can't promise that we never make mistakes, we can say one of these 2 good things has to happen. Either we don't make a mistake, or if we do make a mistake, we learn from it, we make progress. And that's sort of what's going on here.
So the right? Then you never have to.
I might have to restart, right? Like it could be that the majority is always right, but like some people are always wrong, and it's a rotating cast of who's wrong. So I might eliminate, like even if the majority is always right, I might end up eliminating all of the experts and restarting. But I still would have made no mistakes, right? Like the fact that it's an upper bound. I make at most log n mistakes between restarts, but it's possible that I don't make any mistakes between restarts. Or maybe I have to make one mistake or something. I guess like it's possible I need to make one mistake between restarts because at the end, I'm just listening to one person.
But in this algorithm, where you have it like PTB dependent, any factor that is PTB dependent on, like, can't have a PTB response. There's multiple choices.
That's right. So opt here, it's a quantity that's only defined like after I've played out the whole interaction, right? Like opt is a function of the instance. And so what this is saying is, it doesn't have, right? So what this is saying is on every instance, the number of mistakes made by the algorithm is at most log n times whatever opt is on that instance.
So if I had T made out of the opt to be made out.
Could be. I mean, there's no assumption here on the rate at which, but like it could be.
For the opt plus one, so what is referring to like say so it could be as the worst case scenario, you have for every single reset, the extra the near term and then after the final reset, they're saying that if that extra makes a mistake, then you're still kind of you're left with all the other efforts, and then you have algorithm. So you have
Yeah, because it's like the algorithm makes at most log n many mistakes before each reset, but it's only like the best expert only has to have made one mistake after the reset, right? So it might be that the best expert makes 0 mistakes, and the algorithm still makes log n mistakes. That's why you have this like +1 here. Good questions. Other questions? Okay. Let's see. So what do I have on this slide? Okay, so like, okay, so we can think about, is this a good bound? So on the one hand, like, we no longer assume that the best expert is perfect. And so to the extent that the best expert makes only 2 mistakes or 5 mistakes or whatever, this is still a pretty good bound. It's saying we're making on the order of like log n many mistakes. And it still has this benefit that we can, it depends only on log n and not on t directly, so we can throw lots of experts in there. On the other hand, remember if n is 1,000, log n is roughly 10. So if the best expert makes mistakes roughly 1% of the time, this is saying we, the algorithm, will make mistakes no more than 10% of the time, which is not nothing, but is a lot worse than 1% of the time. And if the best expert makes mistakes 10% of the time, this is promising us nothing, right? Like where it's like, it says we make mistakes less than 100% of the time. So like if we think of log n as something tiny, then this is still a good bound, but like you couldn't really describe this as doing as well as the best expert, right? Like if someone was predicting the directionality of a stock and they were correct 90% of the time, that would be truly amazing, right? Like, yeah, like that would be an amazing predictive feat. And our bound would be vacuous, right? It would be disingenuous to say that this algorithm is doing like nearly as well as this person who is predicting the directionality of the stock, 90% of the time. So even in this toy model where it's like a binary prediction problem, we haven't yet achieved the goal we set out to do, which is to do nearly as well as the best expert. We've shown like it is possible to prove a bound that relates our performance to that of the best expert, but at the moment, in some respect, it's an okay bound. Like it depends only logarithmically on n, but like the fact that the log n is multiplying opt makes it actually sort of a bad bound. If this looked something like, if this sort of was more like opt plus log n many mistakes, then it would again be a great bound, right? Then it would say, if the best expert makes mistakes 10% of the time, then we also make mistakes 10% of the time, at least if we run the algorithm for long enough, right? If this was additive rather than multiplicative. So that's sort of what our goal for next class is going to be, to try to get something that like we can truly say does as nearly as well as the best expert with a straight face. And sort of what I want is that if I look at the limit as time goes to infinity, and hopefully I even get good rates and don't have to abuse limits too much, that the fraction of times our algorithm makes a mistake is sort of equal to the fraction of times the best expert makes a mistake, which is something that this bound does not give us. And maybe just in the spirit of having you guys come up with the algorithmic ideas, like this algorithm was super dumb, right? Like in particular, like what we're doing is we're just like entirely crossing out anyone who's ever observed to make a mistake. And then when we find that we've screwed up and eliminated everybody, we forget everything we've learned and just bring everyone back. So what would be something we could do that would be smarter than that? Yeah, so like at the very least, we probably shouldn't like periodically forget everything we've learned, right? Like if it is the case that there's some expert who's consistently, successfully predicting the outcome like at a rate of 90%, like we shouldn't periodically forget that.
Try waiting the evaluation.
Yeah, that's a good idea too. Like at the moment we're sort of, we have this sort of very binary decision process. Either you as an expert are in good standing, in which case we allow you to participate in this majority vote, or you're not. We've entirely eliminated you, in which case you have no vote at all. Which made a lot of sense when there was like a perfect expert, because if you ever made a mistake, like that was a proof that you were not the perfect expert. And we were, why should I listen to someone who's, like not the perfect expert I'm looking for? But when there is no perfect expert, and in fact, like I can't even identify who's going to be the best expert so far, like at the end, like whoever's the best expert today might not end up being the best expert. Probably like I shouldn't just write people off so quickly as a function of, like some short period of bad performance. But, if you have a track record of terrible performance, also probably I shouldn't like equally weight you with everybody else. Oh, you mean if you have like an expert that like is like just every day predicting the wrong direction, that would be great. You could just like, yeah, you could do that. In fact, like if you want to sort of account for that possibility, you could just define a new expert that is like the opposite of every other expert. So instead of n experts, you have 2n experts. That's only, log of 2n is only log n plus 1. So you only have to pay for one more mistake in the worst case. And now you do as well as not just the best expert, but, the opposite of the worst expert. So this is the kind of thing, by the way, why it's very useful to have like a log n kind of bound. It might be that there are various transformations of the experts that are good ideas, right? So maybe, maybe there's someone who's always wrong. Maybe there's someone who's, right on Tuesdays, but wrong on Thursdays. If you knew that, you could transform them. And sort of one benefit of having a log n bound is you can consider very cheaply lots of algorithms run on top of the experts and do as well as the best processing of them. But yeah, just to sort of finish up that last idea, it would make a lot of sense to let everyone have some say in the decision, but give people more weight if they have good track records and less weight if they have bad track records. Sort of a smoother version of eliminating people. Okay. And that's sort of the core of the idea that we will develop next class to get a better bound. Any questions? All right. It's today Thursday. Yeah, I will see you next week.